It's an honor for me to introduce to Professor Tiago Roux Oliveira. Tiago Roux Oliveira is a control theory specialist, an associate professor at the Department of Electronic and Telecommunication Engineering from State University of Rio de Janeiro. His current research projects are adaptive and extreme control theory and application, as a leading model control system, theory, design, and analysis, and control of system with delays and governed by partial differential equation. On this equation, Professor Tiago Roux Oliveira will give the plenary entitled Extremum and Nash Equilibrium Seeking Truths, Delays and PDEs. Welcome, Professor Tiago Roux, and you can start.
Thank you, Juan, for the introduction. So first of all, I'd like to thank you for organizing the seminar. I know how difficult it is to plan one seminar, and you did it 100 times. So it's fascinating. And I need to congratulate you and your co-workers in this battle, right? So as you mentioned, the title of this talk is Extremum and Nash Equilibrium Seeking. I'm not sure if I'm able to complete the task talking about extreme seeking and Nash equilibrium seeking, but I'll give my best to complete it. And of course, the contribution is to consider infinite dimensional systems in this extreme seeking approach, right? I started to work on this 10 years ago, so uh, the years pass very fast, and I could believe that we completed 10 years work on this. But in the beginning, extreme seeking was limited to ordinary differential equations. So my main contribution is to expand this methodology to consider general partial differential equations, and in the particular case, as you mentioned, transport PDEs or simply delays. So the work starts when I was a visiting scholar in University of California, San Diego in 2014. So I had the opportunity to work with Miroslav Kristic, which is a pioneer and a leader in this PDE control using backstepping transformation. This is the approach that we will assume here to handle the PDEs. And if you are interested to meet Miroslav, next week we will have the Brazilian conference on automatics. So he will be the main plenary speaker. You will have the opportunity to visit him. And the congress will be in Windsor Hotel in Barra da Tijuca. And I can give the information to Juan, and probably he will share this with you. Right. So this is our agenda. It's ambitious agenda, but basically I'll try to give you some details on the standard extreme seeking, going through the gradient approach and to the Newton approach, considering static maps and dynamic maps. And after that, I will start to give you some part of my contribution, to share with you some part of my contribution on considering hyperbolic PDEs, in this case, transport processes and wave process, right? And after that, I will give some words about parabolic PDEs in the case of diffusion PDEs, or even a more complex process when we consider also reaction and advection terms, right? This is interesting because we can, this is basically a theoretical result, but we can find many applications, as you can have a look in these words in boldface, right? After that, I'll give some details when we consider multiple PDEs, and of course, a simple case when we have nonlinear PDEs in this problem of traffic control, right? At the end, the Nash equilibrium seeking in non-cooperative games, and we will give some details on how to expand this extreme seeking approach to this more general scenario involving Nash equilibrium, right? And at the end, the conclusions. So we need to start mentioning that extremum seeking is a model-free real-time optimization method. So we want to optimize things in real time. This is not a offline approach, but it's a online approach. And it's perfect for dynamic systems because we need to do this considering the dynamic nature of the problems. Of course, we will, since we are handling optimization, we will have some maps with maximum points or minimum points. And what you try to do is to optimize this map in the presence of some dynamics, and in particular, in our case, infinite dimension dynamics governed by partial differential equations. So we can think in the problem of maximization of a simple map, or even trying to optimize the derivative of the maps. So in this example, this numerical example, we have a function in blue, which the derivative has an extremum. So this is a different way to expand the classical real-time optimization methods, not to maximizing or minimizing a simple function, but its derivatives as well. So of course, in this talk, we will concentrate our efforts in optimizing the own function. But I'd like to give you this explanation that if you are interested, you can use this approach for optimizing the derivatives of the map as well, right? So in this sense, the function, this map Q, will have extremum. So the gradient in this maximizer will be 0. And the Hessian, or the second derivative of this map, in this maximizer will be less than 0. If we are handling minimization problems, the Hessian, I call this second derivative as Hessian, as you know, this will have a positive value, right? This is an expression that is very useful for us because our results are locally. What this means, that we can prove stability in the neighborhood of the extremum point, right? So in the neighborhood, these maps with extremum points can be modeled by this quadratic function, where the maximizer or the optimizer is theta star, h is the Hessian, the second derivative of the map with respect to theta, and y star is the extremum point. So if you are able to force the input of the map close to the theta star, we are forcing the output of the map to be simply y star, which is the extremum point, right? So we're going to consider maps with one input and one output, but we are able to do this for multiple inputs and one output when we are talking about extremum seeking. And when we are talking about Nash equilibrium seeking, we are able to consider multiple inputs and multiple outputs. In this case, the multiple inputs will be the actions of the players, and the outputs will be the payoff functions, right? I hope that we can have time for that. So basically about standard extremum seeking, we can show this block diagram. We have the map that we want to optimize. There is no dynamic in the plant, as I mentioned before, so far, okay? What we need to do is to find the correct input, theta, which you know is theta star, so that the output of this map goes to y star, right? This is the basic elements of the extremum seeking controller, right? So you can see that we have an integrator. Here we have an adaptation gain K. And here we have a demodulation signal and an additive jitter, right? These signals, they are very important. They are simply sinusoidal functions. You can check here in this part of the slide. And what they do, basically what they do is to try to estimate the gradient of this function in this point so that we can adapt the output of this block so that we can lead to the gradient to 0. If we lead the gradient to 0, we are basically find the optimizer. This is simply what you need to do to know about this gradient-based extremum seeking approach. So I'll give you more details. We, of course, can state estimation error. Ideally, what we want to do is to bring this theta tilde to 0 to a small value so that we can estimate the correct theta star. If we write the error equation, the dynamic error equation for this problem, we can obtain basically what you do is to compute the signal what is reaching the input of the integrator once the derivative of theta tilde is the same of the derivative of theta hat. So the input of the integrator is simply k multiplied by g. G is simply y times m, as I write here. Okay? If you plug this expression here, you can obtain this one. But the bad news is that it's very hard to analyze this equation, but there is a good news. If you write the average system, the equivalent average system, and in this part we need to recap the average theorem. The average theorem means that if you have a system and you can compute the average version of the system, like this expression, if you prove that this average system is exponentially stable, there will be a periodic solution which satisfies this expression. So, since the average system is exponentially stable, we will converge to this periodic solution, which is of order of 1 over omega. Omega is exactly the frequency of the signals that we are using in our case. So, in this case, we can conclude that the original variable will be close to this periodic solution, and this is of order 1 over omega, right? So basically, if you prove that the average system is exponentially stable, you prove that the original system is converging to its equilibrium except for a residual error, which is controllable. So in this case, the average version of this right-hand side is exactly k bar theta tilde AV. I represent the average versions by this subscript, right? And k bar is simply kh. H is the Hessian, and k is the gain, the adaptation gain. Okay? If you choose this like a negative value, right? And we know this by assumption that h is negative in the maximization problem, we simply need to use a positive gain k, and we can conclude that the exponential stability of this, the origin of this equilibrium, and as I mentioned before, invoking the averaging theorem, we can prove that the error between theta, the input of the map, and the optimized theta star is bounded by this residual set, which depends on A. We can choose small a, and on 1 over omega, we can choose simply omega large, and we can decrease this error and satisfy the control objective. In the Newton-based approach, the novelty is that we are including a Riccati filter, right? So we need to use this different multiplicative jitter n, which is given by this expression, right? This is not magic. This comes from some results in the literature. But when we do this with this Riccati filter, we can estimate not estimate for the Hessian, but for the inverse of the Hessian. In this case, when we multiply the output of this filter by G, we can kill the dependence of the convergence of the algorithm of the Hessian. For example, if Hessian is small value, the convergence will be low according to this expression, right? But if you kill the dependence of H, we'll obtain a user assignable approach. If we increase K, you can improve the velocity of the controller, right? This is what clearly we have in this expression here. Perfect. I hope you are following. Now we'll go to give some words on the dynamic maps. Basically, there is a dynamic here in cascade or in connection. I think this is the best word with the map that we have an extreme. Basically, in this case, when we have ODEs, ordinary differential equations, we need to establish that this combination FH has an equilibrium such that X is like a steady state, right? And this steady state, here represented by L theta, is locally exponentially stable. When we compose the functions X and Y, we obtain this one. And this has the same form that we considered before when we assume a locally quadratic map. Okay, but how we can do this? Simply, we need to choose the frequencies of this perturbation signals such that we use now low values, not high values. Okay, and in this case, we can separate the time scale of the dynamic part of the system from the dynamic from the static part of the system, right? Of course, we can do this rigorously using averaging, and of course, now we need to consider singular perturbation. Okay, and the theorem is a little bit different because the residual set now not depends on 1 over omega, but depends on omega. So if you want to do the residual error is small, you need to choose omega small. But there is a consequence. The convergence rate is smaller as well. There's no free lunch. You know about that. This is real life. When we consider hyperbolic PDEs, the simplest case is to consider transport equations or simply delays. The first work on the journal publication on this topic involving extremum seeking delays was in our transaction automatic control paper in 2017. There we consider the gradient and Newton versions for constant delays. We have considered maps with one input and one output, and of course the more general setup when we consider multiple inputs and just one output. But there is an important advancement when you consider multiple inputs because we can consider distinct delays in each input. Okay, after map. So this is the main modification that we have when we look at the previous slides and we go for this slide when we consider delays in the output of the mapper. We call this like sensor delays as well. Of course, the delays could be in the input, but just for illustration, I consider here. And what I need to mention or what I want to mention to you, when I consider delays, I need to take two measures. One measure is to delay the multiplicative jitters that we were considering before. I know that you remember the notation M and N, M and N. They are the same signals, but they are time shifted. Okay, and since we are delaying the output, the estimate of the gradient will be delayed, right? So what you need to do, we need to use a kind of predictor to compensate the delay, and so that we have in the input of the integrator a non-delayed signal, right? If you compute the equations, you will obtain this expression analogously, right? With the delay, it's clear here. If the delay is arbitrary, we are considering arbitrary delays, or better, arbitrarily long delays. We are not considering short delays, right? So in this case, I cannot state that this average system is exponentially stable because of the delay. On the other hand, if we compensate through the predictor, we can kill this and return to the first slide, right? So, but how we gonna design the predictor? We can obtain the predictor looking to this expression, right? And if we apply the variation of constant formula to this one, we can obtain a future state or a future estimate of the gradient, which is given this expression. As I told you before, there is no magic here. We can do this, and we can see that estimate, this future estimate, is implementable because it is given only using available signals. Basically, if you want to predict a signal, you use the signal in the current time, and you need to compute the convolution between t minus d and the current time, right? Sorry, the initial time. So we consider the future time as the current time, and we consider the current time as the initial time. Okay? And of course, if you plug this in this expression, you're gonna compensate the delay, and we are done, right? This would be the expression of the control law at this point between the brackets, right? And I simply plug this expression here. But you can notice that I include a filter here. There are two reasons to consider the filter. As I mentioned before, we have to use the averaging theorem to prove stability. But in the case of functional differential equations, we have a distributed delay term here, right? I cannot apply the classical averaging theorem, but I have to use something which is oriented to infinite dimensional systems. In this case, fortunately, I have this result from Haley and Lunel that I will use here. In general, the result from Haley-Lunel is much more general than only functional differential equations you can use for partial differential equations, as you're going to see in a couple of slides. And this is the first step, because when I include this filter, I'm simply transforming input or output delay in a state delay, because now if you move this to S plus C to the right hand side, the left hand side, I'm transforming this variable u as a state variable for the closed loop system. So we have the state which is related with the integrator, and now the state related with this filter that I'm adding. And in a good news of using this filter, I have no time to give details about that, but when we include this filter and we use C sufficient large, we can guarantee some inverse optimality results. In other words, we can improve the performance, the rate of convergence, eliminating some oscillations, undesirable oscillations, just including this filter, right? And this I would like to call your attention. I focus on showing that we had to take two measures, right? Including the predictor to compensate the delay in the gradient, right? And we have to delay the multiplicative jitters, right? The other way that we can avoid this delaying the multiplicative jitters is to try to move the output delay to the input. If we do this and we take additional step in order to try to move this delay to the input of the integrator, we need to compensate the delay in this additive jitter. In this case, we need to advance in time the additive jitter. You can do this because this is a sinusoidal function, it's just a phase shift. So it is equivalent, delaying the multiplicative jitters or advancing the additive jitters. Okay? So this is our theorem. I can show you that this is the state, the theta tilde, the estimation error, and now the state of the related with the control signal, because we included that filter. And we can guarantee if you choose C sufficient large and omega sufficient large, there will be an unique exponential stereo periodic solution denoted here by this, satisfying this expression, right? And then invoking the Haley-Lunel averaging theorem for functional differential equations, we can prove that theta tilde and u will converge to something in this order, right? And with this in hand, we can prove this final upper bounds for the error in the estimation and the error of the output. Take a look on this one. I'm saying that as t goes to infinity, yt is approaching y star as desired, with an error of order a square plus 1 over omega square. Again, if you choose a small and omega large, we have a controllable residual set. Some sketch of the proof, I can write the aerodynamics as I did it before. And in particular, I want to call your attention how we model the delay is using this PDE formulation, right? This expression is equivalent to this one, okay? And if you compute the derivatives to obtain the dynamic system, we will obtain this one. We can represent this as a cascade of the transport PDE with an integrator, right? We integrator of the error if we compute the derivative of this one. Okay, and it's very clear when x, the special variable, is 0, we have the delayed signal 1 ut minus d in this in the output of the PDE, and when x is equal d, this term will cancel this one, and we will have simply ut as we have here. Okay, this shows that indeed we have an infinite dimensional system, and of course, having this infinite dimensional system, we need to find some approach to prove the stability of the closed loop system. As I mentioned before, we handle the PDEs using backstepping transformation. The good news of backstepping transformation is that we have two things with just one shot. We can obtain the controller, in our case for delayed systems, the predictor, and to obtain the Lyapunov functional that we use to prove the closed loop stability. So this conjunction, backstep transformation, Lyapunov-Krasovsky functional, and the average infinite dimension give us all the tools to prove the stability of the closed loop system. I'll give some more details when we were talking about the parabolic PDEs, and so that we do not make the presentation so repetitive, okay? Here we have some simulations. I just want to show you that when we don't have delays, the classical extremum seeking indeed brings the output of the system, of the output map, to the extremum. When we have delays, but we do not compensate it properly, the system goes unstable. And of course, when we apply our approach, we can, after some units of the delay, we can recover the extremum as desired. This is why I show you some, the blue ones are the classical one, right? Extremum seeking without delays, and the red ones are the extremum seeking with prediction, right? And in special, I want to show this signal that shows that our averaging based estimate of the Haitian is indeed very effective, because we are estimating the unknown Haitian with this approach. What about applications? So this is the main application that we have for this extreme seeking for time delays. We know that this neuromuscular electrical stimulation problem is very hard to model, because simply we need to model the neuromuscular system. But we know that in some open loop tests, we can see that the responses of the neuromuscular system is time delayed. And basically, when you put an electrical signal in the muscle, the response came with a delay. They are small, but they are there. So we need to compensate this in some sense. Our idea is to provide closed loop feedback system to help people to rehabilitation, stroke patients for rehabilitation. The basic idea is, if external seeking is not based in models, and we now can handle delays, we can provide a feedback structure to adapt the gains of a PID controller, which is a classical controller, proportional, derivative, integral controller, so that this controller with adapted gains through the external seeking approach can find the best gains which we need to help the people to do some desired trajectory. This is our apparatus that we have constructed. This is the electrical stimulator, which is running our external seeking and PID control. Basically, what you have here is a goniometer to measure these elbows position, and these are the electrodes that we put in the biceps and the triceps, when we provide some stimulation to the biceps, we do this flexion movement. In the triceps, this extension movement, right? So these are the actuators, and this is the variable that we measure, right? And the problem is giving a desired trajectory so that the patient can do repetitive movements through this mechanism, right? So we have a block diagram. So we measure the elbow's angle. We compare with the desired trajectory so that we can establish the movement that we want. We generate an error. This controller is a combination of extremum seeking and PID so that we can stimulate the muscles so that we can try to decrease this error and achieve the objective function. Objective functional, objective control, right? So as I mentioned before, the idea is to state a cost function so that we apply the extreme seeking to minimize this function. If we are doing this, as a result, we believe that we are finding the correct gains to be used in the PID control, right? We can see that we have some cycles of movement. So we establish this square wave in many cycles, right? This is one cycle. This is the second cycle, the third cycle, and so on, right? This is equivalent to do this flexion and this extension movement, right? And we can see that when you turn on the controller, and we are not, we still did not have time to optimize the system. We have this kind of oscillatory responses. But after some cycles, the gains are adapted, Kp, Kd, and Kd, Ki, sorry, and Kd, according to the minimization of the cost function, and we obtain favorable responses, right? Here you can see the control signal, and in red, the electrical signal, which is stimulating the biceps, and the green one stimulating the triceps. If you have doubts about that, I know that probably it's too fast to understand. I can explain better in the end of the presentation, right? In the questions moments. So some more applications I will give you at the end. They involve traffic control and non-comparative games. I think the best option now is try to move forward, and then we go back to once you have already understood all the scenario, right? So going to a more complicated process, a hyperbolic process of second order, we have wave equations. Basically, what we are doing is to replace the transport PDE by a wave PDE, and you handle this kind of system, a cascade of PDE with a static map that we want to maximize or minimize. In this case, maximize. The results were published in this paper, right? Of course, I can share the slides with you and one you give you this to you, and you can check all the reference in details. So at this point, I believe you already understand that when we have a PDE, what you need to do to compensate the PDE in the input of the integrator, and we need to change the signals M or N, or simply compensate the PDE in S. The idea is clear. If we move this block to this point, we cancel the effect with the wave PDE compensator. And of course, we need to compensate the effect of the PD in the input ST as well. Okay, so here we have we show the difference when we change the transport PDE or the delay by this wave PDE. These are our equations now. You can see that we have a second order hyperbolic PDE. Something that I call your attention is that now we are not actuating directly in the boundary alpha dt, as in the previous case when we consider the Dirichlet approach, but we are using, or we are considered the input of the PDE theta as the special derivative of alpha dt. So we are handling the problem and consider Neumann interconnections, right? And in this red footnote, I call your attention that this is the signal that we will obtain when we try to compensate the PD in the additive jitter. Basically, what you need to do, if in the first slide, when you consider classical extreme secant, you have S equal to A sine of omega t, what we are doing is that in the input of the map, we are reaching A sine of omega t. So the idea is the same. We still need to reach the input of the map with the perturbation A sine of omega t. But now we have a PD. The problem is called path motion planning or trajectory generation problem. And what does it mean? We need to find the correct input or the correct S so that passing through this PDE, we reach A sine of omega t. And this is the solution to this problem when we have a wave PDE. Okay? Here we define the estimation error as we did before, and a propagated estimation error, which simply is this theta tilde propagating through the PDE, and we obtain this in the output of the PDE. Okay, this is useful to the analysis, but basically it's the same. When theta hat goes to theta star, we have capital theta hat going to theta star, capital theta star. But in the wave problem, theta star and capital theta star will be the same. They are the steady states of the system. Okay, it's like an equilibrium. So when we consider the second order hyperbolic PDE to model the wave process, and we of course we will obtain a different compensator for the PDE, and this is the compensator. We can notice that is much more sophisticated PDE boundary control, right? And this controller was developed in this reference in Journal of the Franklin Institute, and you can check this in details. The part that I insist to mention is that we are using only implementable signals. You need to remember that we don't have access to the values y star, h, and theta star of the map. So we cannot use these variables in the implementation of the control law, okay? So in the case, for example, of the Haitian, we simply estimate it using this multiplication, nt by times yt, right? And this is explicitly given in here. Of course, this expression, we have some functions that are not defined here, but you can find this in the paper. I think I mentioned the paper here in the first slide of this part. Okay, so the theorem is analogously, but you need to pay attention that the norm that we prove the result for the periodic solution is different. Now we are involving the time and the special derivative of the infinite dimensional u, xt, right? And of course, we can prove that bounds for the estimation error or for the output error, but I call your attention that the residual sets for theta is a little bit different than we had before. Here we can see that we have A over omega. This is related with the jitter signal A over omega sine omega d sine omega t that we had to modify because of the different class of PDEs that we are assuming, right? So this will impact in the ultimate bound, but again, the same idea. If we decrease A and increase omega, we can obtain smaller errors, right? We have some plots, 3D plots, showing the evolution of the state. Here it's clear that we are converging to the optimizer, theta star equal to And here is that what I was talking about before. This is the boundary of the PDE when we have x equal to 0. We can see that the residual error has a different amplitude than when we consider the x equal to 1, the other boundary of the PDE. The residual is bigger, but they are converging to the same value theta star equal to. When you talk about the reaction advection diffusion PDE, you're going to see that these values are different. There is no problem about that. This is the nature of the problem, right? Some PDEs, they will have different steady states in its boundaries, right? So here we have a nice application involving optimal drilling control. The idea is to maximize the rate of penetration of the drill. Okay, and I have a very good sentence here about this application. The drill string is subject to axial and torsional effects, much like a flexible rod. Thus, force and velocity propagation that can be modeled by wave equations. So you have a cascade of a wave PDE with the the map which you want to maximize, which represent this rate of penetration. Recently, we have expanded this approach to this kind of problem. We want to do underwater source seeking. We have some source that we need to detect, and we have a sensor in a cable which is plugged or connected with a surface vessel, and this sensor tries to find the source signal, employing this extremum seeking approach in order to maximize the signal which is measured by the sensor, right? But of course, since we have this long cable, we need to compensate the dynamic system we describe the cable. In this case, we can model the cable not by a simple wave equation, but a wave equation with Kelvin void damping, right? When we do this, of course, we need to modify the control, the boundary control, to have a boundary control which compensates waves with Kelvin void terms. Now we are going to parabolic PDEs. The classical one is diffusion or heat process.
2 minutes,
I call
Professor.
your attention to this. Sorry?
2 minutes.
2 minutes. Okay.
Yes, yes.
So I will skip this, and I think I give much details. I'll give just some words about the Nash equilibrium problem, and of course you can check it in the slides, right? Oh, a big skip here. Just a general look at this sketch of the proof. In general, what we are doing, we write the original closed loop equation, we compute the averaging, then we apply backstepping transformation to obtain the controller and to obtain the Lyapunov-Krasovsky. With this Lyapunov-Krasovsky in hand, we can prove the exponential stability of the transformed system and the original system as well, because this backstepping transformation has an inverse. And then we employ the averaging theorem for infinite dimensions to obtain the results that we need to the original system. But going to the Nash equilibrium seeking, I need to mention Professor Bassar, which is, I think, the most expert in this field with control, right? Basically, what we have delays in the player actions. We have the market in a duopoly game, in this case, with 2 players. We can interpret this like Coca-Cola and Pepsi. And of course, they are trying to maximize their payoffs, right? These are the expressions that we have for the payoff functions. They are quadratic payoff functions, but they are in taking account the delays in the player actions. It is explicitly given in these expressions, D1, D2. In other end, the payoff, in other words, the payoff functions, they depend on the delay, not but for the only one player, but of the all players, right? And one thing that it's important is not interested in maximize a function, but we are interested in find the equilibrium, the Nash equilibrium of these functions. The existence of the equilibrium of these functions is related with the invertibility of this matrix. But the main point is that this is a non-cooperative game, so that each player has access to only these main diagonal terms. And we need to consider some coupling parameters that they can be regulated by a small value. If this small value can be assumed, and each player can estimate its part of this Hessian matrix, we can design a controller. This controller is simply a predictor, as we mentioned before, okay? And we can achieve the Nash equilibrium. Different from the previous approach when we apply Lyapunov-Krasovsky, now we use interesting small gain theorem for infinite dimensionals proposed by Karafides and Kristich in their book in 2018. So, Juan, I think I can finish here. I just want to call your attention that the results that I showed here, they are collections of that we have in this main book. This book was published by Science in 2022, and of course, I'll be pleased if you have a look on this in more details. Thank you again.
Yes. Thank you so much, Professor Tiago Roux, for your excellent presentation. Now, question is open on audio for question. Any question or commentary? Professor Tiago, una curiosity. Extremum seeking in the case parabolic equation, non linear parabolic equation, you have commentary?
Yeah. This is a very good question, Juan. In general, the results of this book is for linear PDEs, right? But we have that first, we have an application here. I will seize this opportunity to show this application. That we have, for example, this nonlinear PDE, which is not parabolic, but it is a hyperbolic. Of course, we need to put some efforts to develop the applications for this case. But in this hyperbolic case, we can see that we can model the traffic control with actuation given by Hemp metering or varying speed limited. And we describe the traffic model by this nonlinear hyperbolic PDE. We have these variables ρ and v. Rho is the traffic density and v is the traffic speed. And if we multiply rho by this function of rho, because the velocity is a function of rho, right? A nonlinear function. This expression, or we call this fundamental diagram, has a maximum. And we have some curves here. And okay, and what you want to do here, if you have a bottleneck, we need to control the capacity in one side of the boundary of the PDE in order to control the flux so that we can optimize the rate of the cars, the movement of the cars through this bottleneck. So this is simply a cascade of this nonlinear hyperbolic PDE with this static map. And we have some observations in the sense that even when we have a nonlinear PDE, we can control this nonlinear PDE locally using a linear control, in our case, a predictor, which is the approach that we presented in the very beginning of the presentation. So there is no problem when we have a nonlinear PDE. We just need to, the first step is try to linearize the problem and to get the equivalent control to the linear PDE that we have. So the linearization of this nonlinear LWR PDE is simply a transport PDE.
Thank you. Thank you. Any question or commentary? Well, if there are no more questions, thank you again, Dr. Tiago Roux Oliveira, for your amazing talk. And see you.
I think we have a question in the chat. One.
The chat.
Yeah, they talk about time varying delays. Yeah, exactly, Pedro. In that problem of neuromuscular electrical stimulation, the delays are time varying. So what is the difference? We need to using a different kind of predictor, which is oriented to the time varying delays. We can consider even unconstant, non-constant delays. I think Jacqueline likes this kind of approach, involving state-dependent delays. We can define predictors for this case as well. Thank you, Pedro, for answering for question this.
Thank you. Any question or chat? Well, thank you again, Professor Tiago Roux Oliveira.
Thank you, Juan. My pleasure.
Bye bye.